In this part of the video, we are going to look at the implementation of a table using binary search tree. So let's take a look. The public interface is still the same. So it's just a table interface. The only difference is we use a binary search tree to implement this table. So now let's take a look. In order for your binary search tree to be built, you have to design your node first. So let's take a look. This is how your node look like. The node has the data part. So this is the data part. This is the data part. And it has two pointers. One is pointing to the left subtree. Another one is pointing to the right subtree. We call it left and right, which just makes sense. Okay, so that's a building block for a binary search tree. Just like linear linked list, it's totally dynamic. You don't allocate a node until you have a data come in, and when you delete that data, you delete that node. Alright, so now let's take a look at this. So it has a bunch of private function, and if you take a look, let's see. You see for insert function, so if you take a look at the insert function, that's where the client will give you a data, then you will insert it into the table according to some kind of searching key or sorting key there. Alright, now you see we have an insert function here. Looks almost identical to this insert, for one exception. The first, you see, the first parameter, it passes in a root. Alright, now I hope you don't confuse this root with this root. So this root is just a parameter, so it's a local variable for insert function, and this root is your data member, so every function have access to it. But now think about it. If in my insert function, when I implement the insert function, if I refer to root, that will be the local variable root, not this root. So first, let's make that one clear. So this insert function just have a root there, and the reason we add one parameter there is we want to use recursion. You will see, like when we do insert, we rely on the recursive function call to solve this problem. And when you do recursive function call, you say, hey, I want to insert it to my left subtree. Then you have to tell this insert function where is your left subtree, and this is what the first parameter is. You tell where is the root of your left subtree, so that it can insert this data in that left subtree. And similarly, you see, for every function, for the remove, we have a remove here with the first parameter as a root, and with the retrieve, we have a retrieve here, and we have a retrieve here. So for every public function, we have a private function corresponding to that function, and we add a root. Add a root as the first parameter. It doesn't matter, it could be the last parameter, but you have to pass in a root to indicate which root, like which subtree you're working on, because it's a recursive solution here. Alright, this is another thing I really want you guys to pay attention to. You see this insert and remove, I'm passing in the root by reference, and for retrieve, I'm passing in the root by value. So remember, when you pass some data by value, you make a copy of it. So when I pass root by value, I make a copy of that pointer. So I have a separate pointer which contains the same address, but that's a separate pointer. Alright. And when we pass by reference, that means I'm passing this pointer by reference. So I don't have a separate pointer. I'm referring to this same pointer. It's very important you do this, because for insert and remove, you can do an experiment by yourself. Just take away the ampersand to see what's going on. Okay, nothing will be added because it's passed by value there, and we will see why there. Okay, so it's when you try to modify the tree, you need to pass by reference. this root. Otherwise, you didn't modify anything. You're just working on a temporary pointer there. And when you try to retrieve something, oh, it doesn't modify the tree, you can just pass by value. So yes, you can pass pointers by reference or by value, and they're different. When you pass a pointer by value, you make a copy of that pointer. When you pass a pointer by reference, you don't make a copy of that pointer. You actually refer to that same pointer. It just has a different name here. All right. So how about now let's take a look at the implementation. Let's start with the insert function here. So let's see, this is a public insert function, and its job is really easy. Just say invoke my private function, and when I'm invoking it, I'm going to tell you where is the root. Okay, and you see here when I refer to root isn't a local variable, it's your data member. Say, hey, here's the root of my big tree. I'm giving you this data, and please insert this data into this big tree rooted at my data member root. Okay, that's what you're saying. And now let's take a look at this private insert function. Pass by value, pass by reference, the root, and the data. So let's take a look at the logic. It's amazingly simple. Just like almost all the recursive solutions, they're simple and elegant, but you know the drill. Usually we don't use them because they're less efficient, but for a tree that will be okay. You will see why later on when we talk about the tree performance, because of the limited number of recursive call there. Let's see. So the idea is if not root, okay. Now pay attention here. When I say root here, it refers to this local variable, not the member root. So it doesn't have to be the member root. For the first invocation, that's your data member root. For the second one, maybe it's not. So it's just a local variable. And for the first invocation, when this public insert function invoked, it's a member root. And later on, in subsequent recursive call, it might not, and most likely it's not. Okay, so if not root, which means my local variable, that means, oh, it's an empty tree. Then you create the new node and size plus plus. It's that simple. Else if that means, oh, I have a root node here, so I'm going to decide where should I insert this data. So I do a comparison. If it's less than, I'm going to insert you in my left tree. How do you insert this data in the left tree? Oh, you do a recursive call. You invoke yourself. You say, insert, I'm going to insert you into my left subtree. That's my left subtree. And if you're greater than me, I'm going to insert you in my right subtree. You see, the logic is really simple. If I'm an empty tree, that's a base case. This is a base case, really simple. I add you right here. And if you're less than me, I'm going to insert you in my left tree, doing a recursive function call, or a recursive function call to the right tree. So that's the general case. Okay, it works like magic. So now let's trace through this magic to see how it works. Let's see. So first time, if I'm still using the integer example because it's easier to do to draw here. So when I insert 60 here, here's my root. So I have a root, and this root is empty at the beginning. So your constructor should initialize the empty tree with a no. So the first time when I try to add 60 here, you invoke this insert with this root the first time around. If not root equal to new node. Good news. Okay, not root equal to new node, which contains 60. So that's 60. And this new node contains no pointer, And so you see, if not root, root equal to new node size plus plus, you're done. Okay, so that's 16. Not very good at drawing here. So now I'm trying to insert 40 next. So I create a new node and try to insert 40 here. So let's follow this recursive call here. You come in here. If not root, that's not true. We do have a root, so you don't go here. And yeah, 40 is less than 60. So what do you do here? You invoke insert with your left pointer. So you do a function invocation. Do a function invocation with, so this is a function invocation, and this is a root, okay? But the root, I'm not going to draw a separate pointer. Actually, the root is this one, is this root, because it's passed by reference. So then it says root left. Then in, okay, so how about I'm going to draw the first function invocation here. The first function invocation, root is here. So if I call it a root, root is right here. It doesn't have a separate memory space for this root. It's just here. So it comes down here. It says, oh, I need to invoke another function with root left. What's root left? Okay, now here the root left actually is no pointer here, but with root left is this guy, root left. So this is root left, but I cannot draw a separate pointer because it's passed by reference. So it's actually this pointer. This is the root left. So for the second function invocation, where root is this guy, where root is this guy here for the second invocation, and it says if not root, yeah, not root. So you go ahead, create a new node and add 40. So you see, it works. But the only reason it works is we did pass by reference. Assuming you didn't do pass by reference, how about that next time? Let's do a let's try to add 80. And assuming I'm not passing by reference, so this is a root. So you invoke a root, okay? For the first function invocation, this is a root, and say if not root, that's not true. So you do another function invocation, and root is a copy of this guy, so which is no pointer. Then when you say root equal to new node, that will look like this. Root equal to new node has nothing to do with this one, have nothing to do with this one. So that's because you're passing by value. So you have to say, I don't have a root here. I'm just another name for this this pointer who invoke me with. So then you can go build your tree here. So that's how insert work. You see, the logic is very simple. If it's an empty tree, that's easy. But when you think about the empty tree, don't think about the big tree is empty. Eventually, you will go to an empty tree. When you do the recursive call, when you reach the leaf, so you're going to add this data as a leaf. So eventually, you're going to get there. So that's why you always add this new node as a leaf. And if it's less than, you insert it into your left tree, then otherwise insert it in your right tree. So that's about insert. Okay, now let's take a look at retrieve. For retrieve, very similarly, so the public function invokes the private function, pass in the root, which is the data member here. Then in the private function, this root is just a local variable. And since we are not modifying a tree, so we pass by value, that's okay. And if not root, when you see if not root, it says, hey, if the subtree, this current tree is empty, you return false. That means you didn't find the match. And then you compare the root item, you see this one can never crush you, because the only reason this one crush you is if root is no, but we already did the checking. If not root, you already return false, so this is perfectly fine. So you do the comparison. If this is equal to 0, string compare, then that means you find the match, you return true. Otherwise, you say, okay, not match, I'm going to look for you in my left tree, or look for you in my right tree or left tree, the recursive function called there. Very similarly. Now let's take a look at delete. Actually, let's take a look at the display function. Let's see the in-order traverse. You see the display function, we want to do an in-order traverse here to display the assorted order. So if root, you do a display left tree, display this one, then right tree. You see this testing is essential. So if you don't have this testing, your program will crash, because this one is your base case. Okay, that's how you end your recursive call and come back. So this testing is so the base case is if not root, you do nothing, but usually we don't like to code it this way. We just say if root, we do something, otherwise we don't do anything. So this, just pay attention to the base case here. You display the left tree first, then display the root item, then display the right tree. So that's display that's an in-order traverse. Okay, now let's take a look at the remove function. The remove function, let's see, very similarly, you invoke the private function with this root, and then you say if not root, that means you don't have anything to remove, you don't have that matching item to remove. Then you do the comparison. If you find the match, you're going to delete a node. You see, delete a node is another private function, because deleting a node could be complicated, depends on what kind of node it is. Is that a leaf? Is that a parent with a single child, or a parent with both children? So that's kind of complicated. So we write a private function, and later on we will focus on how to delete that node. And else, if it's less than 0, you're going to remove your remove it from the right tree or the left tree. So the similar recursive function call. So the only complexity here, there's something different here, is about the delete node. So let's take a look at the delete node. So delete node, so when you pass in this pointer, that's a node. You want to delete the node this target pointer point to. So if not target left and not target right, that's saying I'm a leaf, then it's easy. You just delete target and set target to no. And if you only have one child, so then your child take your place. So this is a code how you make your child take your place, then delete that temporary pointer. And if you else, that means you have two children. So when you have two children, the first thing we do, remember, we need to find the in-order successor to replace you, so that the tree's property still holds. So you want to do that one first. So this is how you find your in-order successor. We're using two traverse pointer. One is previous, one is current. And you see, we first go to target right. Remember how to find your in-order successor. You go right, then go all the way to the left. So you can imagine when you go all the way to the left, it's kind of just like a linear linked list. Just go all the way to the left. It's a linear linked list, and the head is your target right, because you go right, then go all the way to the left. So how to go all the way to the left? You say while current left, you keep on going. So how about let's draw the picture for this one. So how about here, I'm having 60 here, and I have a bunch of, let's just say, the left tree. So I'm not going to draw it. So now let's focus on this one with the in-order successor one. So how about I draw 80, then go 70, then go, how about the 65? Okay, how about let's do it this way. So now in order to find the in-order successor, if I'm trying to delete 60 here, 60 got 2 children. In order to find the in-order successor, we need to go right. So that's one that's bigger than me. Then go all the way to the left. Okay, so here, so we initialize our current. So this is a target. This is a target. This is a target. This is a target thing you want to delete, and your current node. Okay, your current pointer. I'm going to call it current. Your current pointer start with target right. So that will be this guy. Imagine this is a head node for this linear linked list. This is a head node for this linear linked list. You want to traverse all the way here. Okay. And we also have a previous pointer somewhere. So we have a previous pointer initialized with no at the beginning. So now let's see, while current left. So current left, that's how you go all the way to the left. Your previous will becomes current. So that means previous will be here and your current will move on. Your current will move on. So your current will come to here. So then you keep on looping until all the way while current left. Well, so this is current. This is current now. And this will becomes previous. So while current left, okay, this is left, okay, while current left. So when you get out of the loop, that means current is here, current left is no. Okay, then you say target item equal to current item. So you put 65. Remember, this is your target. You put 65 here. So now you put 65 in a safe place and still maintain the tree structure. Our objective is to get rid of this guy. To get rid of this guy, because we already saved 65 there, this node, we need to delete it. So, and when you delete this one, be careful. So if not previous, that means what if that's just 80, so you never need to traverse. Okay, 80 is your in-order successor. If not previous, you're going to say target right equal to current right. Okay, so target right equal to current right. So whatever current right have, 80 has right children. Oh no, or whatever you have. So you make the connection. Else will be previous left. You see, this is previous left equal to current right. And in our case, current right is no pointer, but it could be I have 66 here. Yeah, it could be you have one child. That's why you cannot just say previous left equal to no. You need to adopt the right child here. You need to do that, and then delete the current pointer. So pretty much the algorithm just say, okay, when I need to delete this 2 children node, you go first find the in-order successor. How to do that? It's a linear linked list traverse. So you just go all the way to the left, then try to delete this guy. But remember, this guy could possibly have a right child, so you need to assign this current right to previous left. And also remember this special case. One previous, otherwise this one will crush you. If previous is no, this code will crush you. You have to do it this here. Alright, so that's about the remove operation. And also another 2 things I want you to look at is one for copy table. How to copy table? How to copy a tree? We do a pre-order traverse. So first build the new node, then pre-order traverse here. And how to destroy a table? We do a post-order traverse. So we destroy left, destroy right, then delete the root node. Alright, so that's implementation for binary search tree, and we use a recursive solution because it's not a linear data structure, so it will be hard to write it using a linear loop or something like that. But recursive solution makes it much easier to understand and much easier to implement. The only issue you should be concerned is how many recursive call am I making here, and what does that one depend on. So think about this, and we will talk about the performance next week. Thank you.